since you all had an entertaining view of me trying to operate Zoom, I'll just mention that this is, of course, the Crab Nebula, and it's a composite picture from two telescopes that I have spent most of my tenure at Northrop working on, the Chandra X-ray telescope, which gives you the pale view, the X-rays, and then of course the Webb image on the outside. And that's the lead up to this. If I had to summarize my career in one image, this would be it. This is at the moment, this is the earliest black hole ever captured. It was imaged both by JWST and confirmed by Chandra. So that's kind of what I do. So I'm going to start by telling you about the development of the James Webb Space Telescope. I had a number of positions. I think they're listed later, the last of which was chief engineer. So throughout my tenure on the program, I was responsible for the system design or the technical integrity of the observatory. I've deliberately picked this particular image to be on the title page because it speaks to me very deeply. Number one, it was unplanned release. This was an image that was released when the telescope was finally phased up, but only phased up on axis. And so we had not completed the assembly, but that star was chosen because we, science, thought it was alone and well separated. And of course, it was photobombed by 200 galaxies that were previously unknown to science. And so that, when I saw it, I said that speaks fundamentally to the optimism of this enterprise. We don't know what we're going to discover, and that's why I printed it and put it on the wall of my office to remind myself of just call it fundamental optimism of what we do, what I do. So I'm going to describe Webb's mission. Are there any non-astronomers in here? Okay, cool. Okay, so I can, most of the audience. All right, so I don't feel quite so bad. Occasionally I go to real hardcore astronomy, and telling them about Webb's mission is it's a little weird, but we'll go through, and we'll also want to talk about why it's important. So it's organized around four fundamental themes. The first amongst equals is up here in the upper left corner, and that is the detection of the first luminous objects in the history of the universe. So when things got hard through the development, and there were days that didn't go quite well, I had to remind myself that no matter how hard it got, I was being given the chance with my team to build a machine to see the beginning of time. Now, not quite true, it's the beginning of history, but beginning of time is much more poetic. And if you needed to pump yourself up, let's not be too much of a purist. But central to the mission is the detection of these early universe objects. These are distant, they're faint, they've never been seen before. This is the last great chapter in cosmic history. Because we can literally take the universe's baby pictures, we can watch it grow up and understand the assembly of galaxies. So there's an instrument called the NIRSpec that is able to take hundreds of spectra at a given view angle. The field of view of the telescope is large to collect this data so that we can understand the evolution of galaxies throughout cosmic time. Inside the galaxy, collecting the light that comes out of protoplanetary and protostellar nebula to understand the dynamics of planet and star formation. And then the fourth theme, which I like to call solar systems, ours and theirs, is to examine solar system objects and extrasolar planets to identify them for their conditions, and ultimately, if they're habitable, and get a sneak peek at that. So this drives the design and how the system works itself. So fundamentally put, the challenge was to observe the earliest, faintest galaxies, nearby planetary systems, The fundamental design response writ large, it's a large mirror. Okay, it's large for two reasons. How many of you have had optics classes? Oh, who hasn't had an optics class? Okay, here's a crash course in optics. There's two things that are important, D and D squared. D, lambda over D sets the ability to resolve objects. We're looking far away. Objects are small angularly, they're closely packed. So we need resolution to avoid confusion and know where the photons come from on the sky. D squared is an expression of the light gathering power. As we'll discuss at great length, some of these early universe objects, Webb collects 1 photon per second from. Not 1 photon per second per square meter, but 1 photon per second per telescope. So that's about 400ths of a photon per square meter per second. These are not bright objects. Okay. We operate in the infrared because even though the early universe objects are big hydrogen burning monsters radiating in the ultraviolet and the visible due to expansion of space, that light comes to us in the infrared. Because it's infrared, we need to be cold to minimize the noise. My favorite part of the presentation, we'll discuss that. You'll see why when I get to it. And because of the faintness, we need to be stable in order to take long-term exposures. And so this means stable not only in the ability to point on the sky, but within the telescope itself. So to maintain the image quality, we have to maintain what the optical engineers call diffraction limit. This means that the errors, the average error over any light path, over all the light paths, can be a tiny fraction of a wavelength of light. So when you add those all up, our specification was about 135 nanometers, not microns, nanometers. Okay, and because motion of a mirror involves factor of 2 on that, the physical stability of the structure has to be on the order of a handful of tens of nanometers for up to 10 days. Okay, so we have to deal with things like moving equipment. There's a cryo cooler, essentially a closed circuit refrigerator that cools down the long wave instrument, and reaction wheels, spinning wheels that are quite well balanced, but not perfect. So all of that is some stuff we have to deal with. Additionally, we talked about the wide field of view to get the data that we need, particularly for galaxy assembly. Because we don't know where any of these targets are, we've got to be able to see the whole sky. Okay, now if you've seen a picture of James Webb and you go, how does that work? I'm going to tell you, because I worked on it for a long time. It took me a while to figure it out, so I'm going to share that with you. We've talked about stable optical system. We've also got to be able to get it from the factory to its operating point at L2. So it has to be mass and volumetrically efficient. This is a key part of what makes Webb a revolutionary instrument. And then of course, it has to be reliable and it has to work over its lifetime. And amazingly enough, we're almost 60% of the way through its required 5-year lifetime. Ideas like James Webb, like any of the other flagship missions, they don't fall from heaven fully formed. They have to fight for their right to be chosen. They have to be chosen because they are the most scientifically valiant. I'm sure you could draw a round table analogy with that, but they compete. Over here, almost every program has the canonical napkin sketch. There is a very early sketch of what turned into the next generation space telescope that eventually became James Webb. There were lots of versions of the ideas of how to do this particular science. There's telescope in a tube, which eventually didn't happen. Not very good. Get rid of waste heat. Telescope on a moon still hasn't happened. There were a number of versions. The pictures you see on the right, the upper right was the original TRW mirror design. After we merged our team with Ball, that changed. And then down below was the government, what was called the yardstick mission, which was the government design by which the two competitive industrial teams were measured against. So as we began the proposal and won the award in the early 2000s, in the upper left, that was the design as proposed, and at the CODR, the concept design review. Okay, and it's got a certain clear aesthetic. Somehow it's got that rectangular sun shield that I still don't understand how it works, but that's okay. I wasn't on the program at the time. It's also an 8.5 meter mirror. It was downscoped to 6 meters because of cost considerations. Shortly thereafter, it went down. So we're at PDR, preliminary design review. So this is about 2007. You'll notice, if you look very carefully, you'll see prominent booms holding the sun shield, elegant catenary curves that form the edges. It's a catenary curve. It's the same curve as a suspension bridge. The reason is you can pull on that and it puts even tension into the membrane that holds the sun shield at the right angles that allows it to be the radiative baffle it needs to be. You see solar arrays coming out of the spacecraft on what we call the J2 direction, or perpendicular to the line of sight. As we'll discuss a little bit later, the whole purpose of sequential design is understanding how the system works. So we understand how it fails, and the whole process of design is fixing those failures. So there are a number of failures evident in that picture. Okay, first of all, the solar arrays are in the wrong place. It caused the spacecraft to overheat. So at a later point, as you see here in the critical design review version, solar array is now in the back. That lets the spacecraft dump its heat out the J2 sides. You'll notice that the sun shield has a much sleeker aesthetic look. That's because if you were to sit at the spreader bar there, you could literally look up and see the mirror, which meant the mirror could see the spreader bar, which was a stray light problem. And then my favorite, actually there's two favorites left. If you look carefully around the mirror, you won't see any black closeout. You won't see anything. It's kind of bare naked mirror. Okay, that too is a stray light disaster. That is, light will sneak around the primary mirror, hit the secondary, not coming from the field you're looking at, which is why we added the little black collar called the frill. And if you look carefully underneath, you can't see the deployable tower because that's closed out with a panel, because that region called the core operates at about 100 Kelvin relative to the temperature of the mirror. That's a blast furnace, and it completely overwhelms the signal from space. That all needed to be closed out. And then those, any aero engineering people here? Okay. So you'll like the tab here. It's called the aft flap. It's right by Daniel's name. Okay, that's essentially a trim sail. What that does is, over the field of view, it balances to the extent possible the center of pressure, that is the center of the reflecting area, with the center of gravity, minimizing the overturning torque. Previously, momentum, which is our one most life-limiting item, biggest propellant consumer, was going to be done by adjusting literally the angle of the front part of the sun shield. Terrible idea. It was very difficult to implement, and it had the benefit that it didn't work. So we got rid of it. So this gives you an idea of some of the things that we did to do it. You also see the booms were replaced with a fixed pallet that made the sun shield deployment significantly simpler. Took out a number of mechanisms, a number of moving parts. Ultimately, we had to make one more change, which was the deployable radiator that you see mid back. Let me go. This one's worth pointing to. The deployable radiator that was added. We moved the instrument radiators off the side where they had a significant view to the sun shield, and we were having periodic thermal crises. Every time we would renew the thermal model and understand a little bit better, we would realize that we had underestimated the amount of thermal backloading. So finally, we just moved them out of the way because we were at critical design review. And it was time to get on with the building. So this is the hallmark of a typical complex developmental system. You're learning as you're going, you're fixing things. This is a key part of why new systems are hard. I got a whole talk on that. I won't spend an hour dwelling on it. Just trust me, it's a challenge. It's the greatest job in the world, but it was a challenge. So here are some key features of the final architecture. The fundamental operating paradigm for James Webb is very simple. There is a cold side. The telescope and the instruments live on that. Once the sun shield was deployed, the telescope remains forever in darkness. And the first time I realized that, and I said it in a meeting, one of my longest friends at the company was the telescope manager, and I looked at him and I said, Scott, you know, the purpose of the rest of the observatory is to put the telescope where the sun will never shine. It was funny when I came up with it in 2006. I still get a big chuckle out of it, even though my colleague has now been retired some number of years. But it's easy to remember because it is what enables us to put a large infrared telescope in space without consumable cryogens. So Webb will never run out of cold stuff like Spitzer did and go to a warm and a hot and then end of mission. That will not be the fate of James Webb. So to enable that passive cooling, we needed to separate it from the sun. That's the revolutionary sun shield. 5 amazing layers. And in fact, we came to realize it not only as a mechanical system, but it's really fundamentally a thermal optic machine. And that behavior comes not from the thickness of the materials, but from the coatings and the shapes. So it is truly an optical machine, although when I say that, it just annoys my thermal colleagues, so I don't do that, at least not when they can respond. And so the layers themselves are made of Kapton. This is a polyimide film, layer 1, the one closest to the sun, 50 microns or 0.02 of an inch thick, slightly thinner than a hair, should you have any. And it's coated with silicon on the sun-facing side. Silicon has a more favorable ratio of solar absorptance to emittance. That is, it's very good at getting rid of heat. The tops of each layer is aluminum, which then limits the emissivity and limits the transfer of heat up the stack. That allows us to go from about 350 Kelvin, full sun, to about 50 Kelvin on top. And it's all done with mirrors. Really. The mirrors are made of beryllium. It's a light metal known for both being strong and over the temperature range of the mirror for having a near zero coefficient of thermal expansion. This is important because we had a pretty good idea what the temperatures of the mirrors were going to run at, but if we were a few degrees off, we didn't want to have the telescope not work. So that was an important point. Up until almost the preliminary design review, there was both a glass and a beryllium mirror carried as an option, and then beryllium was down selected.
Where does it emit to space in this direction?
Yep.
And not in that direction?
Yep. So essentially, the sun shield is 4 V grooves. There's actually about a 2-degree inclination to each of them. So essentially the sun, the 300,000 watts of the sun, most of it gets reflected and rejected. of the little bit that gets absorbed. Of course, the top part heats up, radiates in all directions. A little bit more than half of it goes straight out because there's a V. A little bit less than half goes in, gets absorbed, gets re-emitted, and eventually it walks out. And so each of those successive layers are significantly colder than the last. The backplane is also a near zero coefficient of thermal expansion. That was one of the technologies that we developed and showed that we could actually tune that zero CTE crossing and do that with sufficient prediction that we could predict what was going to happen at the rate of nanometers per Kelvin, which is necessary. So usually people are relatively familiar with the other famous space telescope, Webb and Hubble. Hubble's there on the left, 2.4 meter telescope, same size as the Hooker telescope on Mount Wilson. It also, like the Hooker telescope, is a big, thick piece of glass. In order for Webb to do its mission, we needed a much larger mirror, about 7 1/3 times the collecting area. That's not the only difference, is Hubble is quite heavy, 11.1 metric tons. We clearly could not use the same architecture or design paradigm because we would wind up being too heavy to lift. Turned out that the Ariane rocket that was supplied by the Europeans put a mass limit of about 6.5 metric tons. We actually came in at about 6.25. But if you're doing the math in your head, that means at the level of the space segment, the flying satellite, Webb is 15 times more mass efficient in taking a unit of collecting area to space. And it's done that because it took a fundamentally different approach to create the mirror. And here is an example of part of that design. So the beryllium mirror starts out life after it's mined in Utah as a billet, a solid billet of beryllium, 400 kilograms solid. It's pretty heavy. First thing that happens is that solid hexagonal prism gets cut in two like a muffin. And then the next thing that happened is those blocks went to Axis in Coleman, Alabama, where approximately 92% of the material was removed. So that was a technology. Again, we had to machine from the back, had to come through, leave a consistent face sheet so that the mirror could be polished and not have that ISO grid print through. That was done so long ago that almost nobody remembers, but that was big doings in those days. And it was one of the early technical triumphs. And in fact, we had to polish the mirrors to about 20 nanometers RMS error, and they're actually polished a bit better. Another fun technology is the machines and the people that make the mirrors live at room temperature, but that's not the operating temperature of the mirror. And while beryllium has a small CTE at the operating temperature, it's not zero over all temperatures. So we had to understand at the level of a handful of nanometers, what happens when you measure a mirror at room temperature and have to cryo-figure it. So in other words, we measure the errors at cryo and have to translate that into an error map at room temperature. And that process has to have a residual error of only a couple of nanometers. And that was all pioneered and developed and went into production, and the mirrors were finished long ago. Wasn't the only technology. The backplane, the actual algorithms to do the wavefront sensing, which similar to what was on Keck, but not the same, had to work. And of course, the sunshield membrane materials had to be qualified to stand in their environment. And then on the detector side, there were a number of other technologies. My first job on the program was actually running the technology test for the structural article. This is a picture from the front page of the Huntsville Times where it was big news. I'm in the picture, I'm standing right off to the edge of the monitor. When I brought the newspaper home to show my mom that I had made it to the front page of the paper, she said, "Where are you standing?" And I said, "Over here where they're talking about the barbecue at the park," or whatever was in the leftmost column. And she said, "Next time, stand in the picture." And so there I am, clearly recognizable as a white blob in a clean room suit, checking out the myriad of temperature sensors. And what we did in this test was make a very accurate temperature map and relate it to our structural prediction. So it was not enough to show that the technology performed sufficiently well for Webb. In order to show we understood the technology, we had to predict what was going to happen. Keep that in mind, we're going to come back to that. There's another story later. In case you don't have any idea how bloody big this thing is, this is our full-scale model in front of a standard issue German museum. There's a ship's screw and a car over there and a whole bunch of people. And somebody that you can see, and I will stand up to remind you I'm not the canonical 2-meter man. And what's even more amazing is at the time, which was right after the preliminary design review and before the critical design review, that represents 3% of the people working on the program. So James Webb was big in every sense of the word: physical, scale of human effort. Depending on how you calculate it, it's between 80 and 100 million people hours of effort, not counting lower tier suppliers. It's also revolutionary because it's bigger. The mirror is bigger than the rocket it goes in. All right, so we had to fit 6.5 meters of mirror in a 5-meter rocket. We did that by folding it up. And that not even including the 22 by 12 meter sunshade that also had to fold up. So those of you, well, we'll just start with this. We talked about the detecting the first light in the universe. These are very faint, 1 photon a second kind of numbers. So to do that, we have to defeat the noise source that we take with us. This is the light that comes off the mirror in the form of black body radiation. So here we have the northern sky constellation Orion. It's my favorite. Not the least of which it's one of the few constellations I can actually see from my home in Los Angeles. But that's how it looks on a dark night. Okay, and what we don't want is we don't want poor seeing from noise on that. So for those of you that are not physicists, for those of you that are physicists, you already know the answer. So just zip the lip here for a minute. This is for those that aren't. This black body radiation is a fundamental property of all objects in the universe at any finite temperature, which, if you believe the laws of thermodynamics, is all objects in the universe. So to illustrate this and to illustrate why cold, I'm going to call for help from another one of my most favorite objects in the universe, also called Orion. And here he is. Okay, 2 very important observations I want you to make. Number 1, most important, he's a very handsome devil. Okay. Number 2, he's an indoor cat. Okay. So like I said, we do a fair amount of outreach, and we had an infrared camera that we would take to AAS meetings. And so you got it. One day I said, I'm going to take the infrared camera home. I did chase my wife around taking infrared pictures. That's a different story. But I took a picture of my cat. So again, 2 things to remember. Again, the first and foremost is no matter what wavelength you look at him in, he's still a handsome devil. And number 2, more germane to our story, is as a small mammal, his body temperature is 38 or 39 degrees C. Fortunately, the walls in my house are not that hot. You can see the cat, you cannot see the walls. The way you turn off the black body radiation is by making it cold. This is the fundamental reason that James Webb is cold. It is an absolutely essential part of its mission. So that infests the design. We have to have a huge mirror, bigger than a rocket. We want it long-lived. So we can't have a consumable, so we have a passive system. So you can begin to see how the mission informs and drives the design. And you can always remember hot mirrors are bad. For those of you that are coming to the communication tomorrow, this will come back up again. The orbit for James Webb is not around the Earth, it is around the sun, around a position called the second Lagrange point. There are 5 points indicated in this cartoon by green dots. Those are the 5 Lagrange points. They orbit the sun with the same period as the Earth. In the case of 3 of them, that's not terribly surprising. There's 3 of them on the Earth's orbit. Should not be surprised, because Kepler says distance from the sun tells you how long the period is. But the interesting ones are the ones that are in line between the Earth and the sun, so-called L1 and L2. Okay, these are at different distances. So if you just dropped a random test particle in 1,000,000 miles, which is where L2 is, it would take 374 days to go around the sun and eventually drift away. Because Webb is precisely injected, it stays in proximity of the Earth. And this is an absolutely key part of the system design. It does several things. Number 1, the Earth stays close. This is close in angle and close in distance. So this way we can phone home with the data and pick up the phone and get commands. And it's kind of standard, not quite textbook, but as off the shelf as space hardware gets. That's an easy part. The flat sun shield can hide the sun, the Earth, and the moon, the brightest objects, because they all remain below the horizon of the sun shield. And the flat geometry allows Webb to radiate its heat to space, getting to its operating temperature of approximately 45 Kelvin. So again, the mission design all fits together, right? And if you say, why can't you orbit the Earth? Think about an Earth orbit. There's part of that orbit, if it's large enough and you're above outside the orbit of the moon, there are points in that orbit. Yes, absolutely, you can hide the sun, Earth, and the moon behind the sun shield, but there's also half the orbit where you can't. And if we put a hat on it, that spacecraft in a tube, telescope in a tube that you saw earlier, can't get rid of the heat, which means you can't do your science mission. So it's an inferior design, so it was not selected. So how do you see the whole sky with this crazy looking thing? And why is the sun shield that weird shape? It is weird. It's very beautiful, but it's a little weird. So we have a number of requirements to see the sky. One of which is at the ecliptic pole. That's the pole perpendicular to the plane of the sun or the Earth's path through the sky, to be viewed continuously. So the way that you do that is by designing the sun shield to be long enough that when the observatory is tipped 5 degrees towards the sun, as shown in here, the light from that shadow misses all the structure. Okay, we also have a requirement to see at least 35% of the sky at any given time. So we do that by being able to tilt backwards. We chose 45 degrees because when you do the math and include the fact that you can spin symmetrically around the sun line, that gives you about 39.25% of the sky. Better than requirement. We don't have to quibble over, did we meet it or not? It's a simple, very fun, interesting math problem for those of you who remember your calculus. You should do it by hand. You'll like it much better. So how do you see the whole sky with this? Basically, let me go back. As the satellite goes around the sun, that viewable band called the field of regard rotates and sweeps out the whole sky. In fact, you can see the whole sky in 6 months because you pick it up on the opposite sides. And because we can tip 4 or 5 degrees in front of the north ecliptic and south ecliptic pole, it sweeps out a circle that allows them to be permanently visible. So this next video is putting the observatory through its pitch and roll constraints. On the left is instantaneous. On the right, there's kind of a freeze at the limit. And we're essentially building up the protective envelope of the shadow. So in order to keep the telescope, the instruments, the low gain antennas, the other little bits and pieces of structure in the shadow, that's the limiting shape. And so you get this shadow pyramid or polyhedra or whatever you want to call it. It's a shape, if you will. That shape is essentially big enough to surround the observatory, and because we were really tightly packed, it's not terrifically oversized, but it is big enough to do the job. And for those of you that don't think remembering all your plane and analytic geometry is important, we actually constructed that by hand to show that it did cover everything, including all of the alignment tolerances. And it was quite fun because when people said they didn't believe it, we just gave them 35 pages of math. Here, check my math. That's a whole nother.
About 15 minutes.
Okay. Yep. So we want to talk about how all of this happened. In other words, how did we go from a pencil sketch that I've already showed you? On the right-hand side, that is, if you look very carefully, you'll see someone you recognize. That is the Northrop part of the Webb team receiving the Collier Trophy in 2022. That's the highest award in American aerospace. You can go visit at the National Air and Space Museum. You'll see James Webb team on there. You'll also see Orville Wright, Apollo 11 and Apollo 8, Chuck Yeager, number of people that pretty familiar in terms of aerospace. So this is pretty much the high water mark, and it was fun getting dressed in a tuxedo. Any musicians in the audience? Okay, how do you get to Carnegie Hall? Practice, practice, practice. The same way you get an observatory to L2. So here is about our clean room in about 2006. And you see a mock-up. And we were practicing operating those giant lifts around a mock-up that wouldn't get hurt if we ran into it. Because we need to get technicians all over, but the JLG lifts and the other cherry pickers are not designed to be super precision. So we had to train operators, had to understand how to fold things up, pick things up, turn them over. And so you don't want to do that on flight. You don't want to be the guy that drops the telescope. Here's the sun shield. So the yellow plastic you saw before was the 0th version of the sun shield. It was a couple of layers just for, this is now 5 layers that look nearly flight-like, with the exception of this one didn't have the silicon coating because that was very expensive and rare. So that's a full-scale model. No technician could touch the flight model until they were checked out on the Pathfinder. 2 things in the back. These are very thin membranes, so you can't walk on them. So in the back, there on the left, you can see what looks like a jungle gym, and that's actually a telescope simulator, including, if you look very carefully, you'll see a very elegant model of a primary mirror with the gold. That's actually styrofoam with gold gift wrap on it. We got the colors because we wanted to understand the reflections and to make sure that people could reach, and we could actually insert technicians on what are called diving boards on the end of forklifts, and you'll see that in the movie in a little bit. The 3rd scale sun shield in the back was actually tested in the chamber for its thermal performance and found out that it worked a little bit better than we had anticipated, which was bad because we couldn't explain it. We couldn't decide whether we couldn't take credit for the overperformance without taking penalty for the potential underperformance. So we went back in and found some missing physics. Also did a fit check when we were able to get structures together to make sure that things fit together. practice putting the mirrors on. My backplane support test article got repurposed. Right there's a Pathfinder telescope that then went off to Johnson to check out test procedures and equipment. And then here go the mirrors on the flight structure. That was so well rehearsed that actually finished ahead of schedule, significantly ahead of schedule. Here we are in the clean room before everything was assembled. On the left is one of my proud achievements, the design of a bag to go around it. If you had told me when I went to grad school, I'd be bragging at a university trip about designing a bag, I would have thought you were in it, but it's true, I'm here bragging. Because that enabled us to get the hardware out of the clean room and across our campus to test facilities, keeping it clean. That bag stayed on through acoustic and vibration tests, so it actually had a number of significant challenging requirements. Whole lot of other things I did. That's only a small list. So it was quite a busy 15+ years, including some things that I didn't expect to get to do. A lot of outreach. I was in a couple of movies. I'm actually media trained. Lots of tours. Quite fun, actually. Here is a video that we're going to watch most of the actual hardware that's in our clean room, deployed for the last time before it got stowed up for flight. Here you can see the wings being deployed on the final time. I told you about the technicians on things like diving boards, on forklifts. There was not a single collision. Everybody knew, it was very well practiced, very well rehearsed. Here it is getting stowed. Leaving our clean room in a shipping container, which is actually a completely self-sustaining clean room, environmentally controlled clean room. Going down Century Boulevard, going to the Seal Beach Naval Station, onto the boat. You ever wondered what a tugboat does? You're about to find out. And there we're going out of the Seal Beach Naval Station, down to South America through the Panama Canal. And here it is coming out. I'll recycle it when we're taking questions. So another very important part of Webb's legacy was pioneering verification, that is convincing ourselves that the whole system was going to work. Webb is too large and too complicated to actually be unfolded and tested thermally in a chamber, so it was tested in pieces. Those pieces were stuck together with the system model. In fact, it was system models, which was a major step towards verifying future, even more complicated, intricate systems. So all in all, to get 6.5 meters of telescope and a 5-meter fairing, it required 178 releases, 50 deployable structures. They all worked exactly as they were supposed to the first time, the only time. That's something we are very, very proud of. On the day of first science release, I remember first time I gave some of these talks, people were very excited about the program, but it was very early. And I remember somebody saying, well, will we know when it happens? And I said, yes, win or lose, we will be above the fold on every paper. You won't miss it. We didn't miss it. There it is on a sampling of papers around the world. Here's some of the first light images that you've seen. I'm not even gonna attempt to talk about the science to a group of astronomers. It's always dangerous. This was, again, a solar system observation. This was the first time Neptune's rings have been imaged since the flyby. This was a centaur that occulted a star, and Charlico actually has a double ring system, and we were able to clearly image and measure the transit of the double rings. Jupiter with labels. The water plume from Enceladus, again, this is one of the first times it's been imaged. Relevant to here, CO2 on Europa, perhaps from the ocean. Rogues gallery of galaxies and nebula. Of course, the earliest black hole. And can't believe it. I worked on something that made it to a postage stamp. I'm an inveterate letter writer. I write to my wife every day I'm on a business trip. She has hundreds of letters. Now she will have about 250 letters with James Webb stamps on them. We're in the phase here as the ability of and the technical virtuosity of Webb is becoming available to the science community in the later cycles. We're now moving from the cycle 0, which showed how well Webb was working. That was the point of the early release science, making a few previously impossible measurements, and now starting to assemble those discoveries into scientific results, right? The understanding of the early universe is not nearly what we thought it was before the mission was launched, and of course that was the purpose. That brings us back to the enduring optimism of that first image and what Webb will discover in the remainder of its life. And with that, I will thank you for your time and the invitation to come and talk to you.